So, you guys have been learning a whole bunch, and you've been throwing around a lot of terms. A lot of terms have been thrown at you. So, we're going to talk about, in particular, 3 of these terms. One of them is, so it's going to talk about batteries. Anybody can guess what that would be? I heard it. Talk louder. Voltage. Voltage. All right, so we've got voltage. Everybody tell me what the units of voltage are? What do you measure voltage in? Volts. Nice and easy to remember. Okay, what's another thing we often think about when we're thinking about voltage? Current. Beautiful. What are the units of current? Right, the ampere, or we often just call it the amp. And there is a thing that relates these two a lot of the times. A super important part of electrical engineering, super important part of physics. And all right, he's ahead of the game here. So resistance. Good job. Anybody know what the units of resistance are? Ohms. What's the symbol for an ohm? Capital or lowercase? There we go. All right. So ohms, which is the Greek letter capital omega, the last letter of the Greek alphabet. And these 3 things you're going to come across again and again and again and again. So we want to have a really good idea of how they relate to each other. So can anybody describe one of these to me? Anybody describe voltage or current or resistance? I can wait. Oh, I'm back. Which one are you doing?
Current.
All right, what's current?
It's the charge that goes through a circuit over a given amount of time.
All right, so the charge goes through a circuit, so it's moving charge. What do we call those charges? Electrons. So current, we have moving electrons, and the current is the number of electrons that move through. So you have a lot of electrons moving through, you have a lot of current. Only a couple electrons, you have a little bit of current. And the other ones. Anybody want to do one of those? All right, what's voltage or resistance?
Okay, so resistance is sort of like an interference within the circuit that slows down. It's sort of like a bump in the river that will slow down the rate of, it will like slow down electrons sort of.
Okay, so almost. It's not really making the electrons move slower, but you're on the right track. Anybody else?
It reduces like the current, how many electrons.
Exactly. It reduces the number of electrons. So voltage or resistance changes number of electrons flowing. Okay? And the last one, voltage, anybody?
Electric potential difference.
Okay, so electric potential difference. What does that mean? Anybody else?
I think it's like the change in potential energy over the total charge.
Okay, and what does that mean? You give like kind of a more, like if you're like trying to explain it to like, you know, your younger sibling, like what would you say?
It's kind of just the change in energy.
Okay, and what does it do when I like, you know, apply a voltage? What is the cause, like what does it cause to happen?
Stronger current, more energy.
So stronger current, and if we have a stronger current, that means more what? Electrons are moving, which also transports more energy. Excellent. So the voltage is what is making the electrons move. So makes electrons move. Okay. And we've got some relationships here. Yes?
So is it basically a force, or?
So the voltage isn't a force, but it creates a force. So there is a relationship between voltage, and voltage acts on charges and creates force. Now I know some of you have seen the term EMF today, which stands for electromotive force, which is somewhat unfortunate because back in the early days of physics and engineering, we didn't really understand all of this stuff, and so they came up with this term electromotive force, which is really voltage and isn't really a force. Welcome to your first chance of like historical names that don't make sense anymore. You'll encounter many of them in college. So, voltage is not a force, but it does create a force. Now, let's think about an analogy for how these things interplay. And you guys have already said some pretty good stuff here. So, if we were to imagine that all of you were electrons, alright, so you're all electrons, where do electrons hang out? In atoms. What else is in atoms? Neutrons and protons. Alright, excellent. So, we've got these atoms, right? And when you have atoms and you put them all together, they'll make some sort of material, right? So like your wires might be copper atoms or tin atoms. And you know, we have our rubber mats here, we've got all stuff made of different types of atoms, different atoms and different properties. So some properties, some atoms have kind of these extra electrons that can move around nice and easily, and that's where we get a conductor. So in a conductor is made of atoms, like metal, that have these extra electrons that can move around nice and easy. So imagine like you're these metal atoms, or these metal electrons. You're in this metal, on these metal atoms, and I want to make you move, alright? So I could say, hey guys, I mean I know you really like me, so if I just ask you, could you just like run around the school and come back in right now? I haven't seen you move yet. Well, I'm kind of disappointed. Well, okay, so I haven't really given you much incentive, right? Like, you're like, I mean, I guess you seem like an okay guy, but not that okay. So, you don't really have much incentive to move anywhere, right? I've got to give you some kind of incentive. Okay, so what if I told you, alright, if you go outside, you run around the building, and you come back in this door, and you sit back down, and then you get up and you do it again, and every time you do that, I'll give you 30 cents. Would anybody do that? Got at least 1, 2 people? Okay. What if I give you $1 every time you did that? A couple more people. Okay. Alright. A couple people are like, nah, I'm pretty lazy. So, what if I said you gotta run around and I'll give you $100 every time you do a lap? Alright, he's like, I'm on this. Alright, I'm pretty sure like all of you would do this for $100. Now, I didn't really say, I said I wanted you to run around the school and come back in, but I didn't say exactly how far I wanted you to run. Right? So what if I said I want you to run up to, let's say, Google's campus and back for $1?
How far?
Anybody?
No.
How far is it?
How far is it?
I don't know. Who knows how far away Google is?
A few miles.
A few miles, yeah, a few miles. So maybe, I don't know, we're talking like 4 or 6 miles round trip.
Pretty far.
Anybody down for $1? $10? $100? Okay, here we go. All right, $1,000? Yeah? Okay, $10,000, everybody? All right, cool. All right, so enough incentive, you'll run 4 miles and back, right? Yeah. So think of like that money is like voltage, right? So if you take a wire and you set it down, right? It's not going to do anything. Like those electrons are just like, meh, I'm just going to chill here. But then if you take that wire and you connect it up to a battery, that battery creates a voltage. And that voltage is this incentive for the electrons to move through the wire. But, you know, all of you guys were kind of thinking of like, I'm just going to go quick around the building, and for like $1, a lot of you would do that, or for like $10 or $100, pretty much all of you would do that. But when I was like, oh, why don't you go to Google and back? You're like, I'm going to need some more money for that. Nah, So, the thing that means that you're going to need more incentive is this resistance, right? Like you definitely feel a resistance to running 4 miles. So, if we have more resistance, we got to have more incentive to get the same amount of behavior to get you guys to go out and back, or to get the electrons to go out. And what is the way that we relate these 3 variables? I know some of you have looked it up already. Raymond?
We are
What's it called?
voltage equals current times resistance.
Right. So we have V, voltage, is equal to I, current, times resistance, R. Everybody know the name for that?
Ohm's law.
Ohm's law. So this is called Ohm's law, named after Ohm, who is also where we get the unit for resistance. And a device that follows this We call it ohmic device. Alright, let's look at a real simple circuit here. Alright, you guys have been dealing with batteries. What kind of batteries are you using?
AA.
AA, 9 volt. Alright, how many volts is in a AA battery?
1.5.
1.5. So I've got a AA battery. Alright, which is the positive side?
The
Pointy.
Who thinks
the
it's the
top
top?
one. The top.
Who thinks it's the bottom?
No.
Hey, Eric over here. Shh, could have fired him.
They don't teach those mechanical engineers anything.
He's mecking.
You can see, right?
Alright, so this is the positive side, this is the negative side. This means this is the higher voltage. And electrons always want to go from the higher toward the lower. One way you can think of this is, what's the charge on an electron? Negative, okay. So, negative are going to get pushed, well,
Now you're getting in.
yeah, that's true. Let's come back to that later. It's another fun historical thing that doesn't make any sense. So, charges are going to flow from higher voltage toward lower voltage. My current is going to flow. Okay. And if I just put a wire directly, that's not really good. We call that short circuit, right? But if I put a resistor, then that's going to lessen the amount of current, because that's going to provide some resistance. That's like increasing the length I want you guys to run. So let's do a quick calculation. So if I have 1.5 volts here, and I have 150 ohms, okay, how much current is going to go through this circuit? 10.
Wait, no.
So how would I figure this out? What am I solving for?
0.01, like 100.
Okay, so I'm solving for I. So I get I is equal to 1.5 divided by 50, and that is
About
0.01. All right, so amps. And 0.01 amps, often if we're talking about small amounts of current, you'll see it milliamps. Anybody know how many milliamps that would be? 10 milliamps. Excellent. So 10 milliamps. And that is a measurement of how many electrons are going through this circuit. Okay. Now, what would happen, let's say, if instead I were to bump this up to 15,000 ohms? How many amps would I have? I just add 2 zeros.
0.1.
So 0.0001 amps, or, as he said, 0.1 milliamps. So it's way more resistance. It means that for that voltage, way fewer electrons are going to go through. Now how could I make more electrons go through? Or increase the voltage. Excellent. So that's the whole idea here, is you have these three interacting things, and you can change the different ones to change how the circuit behaves. You guys any questions about that? Good? Okay. I think we're just about ready to wrap up. I want to make one other point, and that is that the electrons move actually pretty slowly, but they're all kind of like pushing on each other, which means that the effects of their movement move at almost the speed of light. So think of it like a water faucet, right? When you turn on the water faucet, you have to wait for the water. Oh, okay, but the water that comes out, was it just in the ground like a second ago? Where was it? It was in the pipe, right? It was just behind the faucet waiting for you to open it. It was in the pipe. So like electrons are everywhere in your circuit all the time. And when you turn on the battery, and you connect the battery, it pushes on this one, which pushes on that one, pushes on this one, and they all start moving at the same time. But each individual one moves pretty slowly, but all together, the behavior starts happening instantly. And one other word I want to talk about is power. Some of you, a lot of talking about power. Power is a slightly different thing. It's actually equal to voltage times current, and it's a measurement of energy per time. We might talk about that later. But I just want to point out that power is not interchangeable with voltage or current. Power is about the amount of energy and how quickly that energy gets deposited. You can kind of think of like electrons going through here being like friction, right? If you like rub something, it gets warm. You transfer energy to it, thermal energy. So the electrons warm up the resistor, and if you have too many of them, it warms the resistor up too much. And that's the power in the resistor, that's the energy being transferred to the resistor. So remember, there's this other thing that's power that isn't the same thing as these guys here. But I just wanted to quick point that out. We might go over that in more detail later. All right, excellent. Guys, feel a little more comfortable with these concepts now? Beautiful. Then we are done for our discussion today.